All right, our next speaker is Dr. Ron Malone. Thank you, Dr. Malone, for being adaptable to our changes in schedule and things that have come up, and really appreciate you being here and imparting us with some of your vast knowledge. Thank you.
Well, and thank you, Andrea. It's been a great workshop. I enjoyed being here. I've learned a little bit about shrimp.
Okay, good. I hope so.
Hopefully, I'm going to learn a little bit more, too. We came to this workshop last year, sent one of our people up here, and she went back and immediately started raising shrimp, and she sort of worshiped the ground that these guys stand on up here for the whole time she worked for me, so doing a great job. I see I'm coming from a town called New Orleans. It's actually, you know it, I think, without the E, but I'm embarrassed by that. I look up there. I'm Ron Malone. I'm a doctor, previous with Louisiana State University for about 37 years, where I'm an environmental engineer and specialized in recirculating aquaculture systems. About 3 years ago, I moved over to Aquaculture System Technologies, which I'd been technically supporting for some decades, and my brother and I bought the company. So now I'm a chief technical officer. Just one slide on our company. Our clients love us. And our clients are the animals in our mind, so we're always working to protect those little guys. This guy's not so little. We specialize in floating bead filters, and we apply those to recirculating aquaculture, aquaponics, zoos, industrial, and wastewater. And you can see all that on the internet. We have a good homepage up. And then we specialize in these various processes. The reason in this first talk I'm circling this component is in order to sell the products that we produce up here, we conduct what are basically RAS layouts and production estimates. Sometimes in a formal what's called phase one, where you tell us what size building and what your idea is, and we'll lay it out and we'll generate the paper numbers out to how much money you're going to make or lose. About 50% of the people that take the time to do that don't buy in when they look at the profit margins and look at them from the light of a conservative engineering firm. So that's something I'd suggest to all of you that are starting, is find somebody that is technically qualified to go all the way out to a realistic economic analysis so that you can see where you're going to be 5 years from now. Because of that, we're involved a lot in buildings. We don't actually do buildings. We usually work with local contractors. But we give them a lot of advice on what to do and not to do with those buildings, mainly because of our experience over the years. I've been in the business for 40 years. We can tell you the stories about what happened to the last guy that didn't pay attention to this, right? So that's what I'm going to try to particularly bring to your attention. First of all, if you come to us and talk to us, you're going to see a system design that's fractal. And we're doing this strictly for disease control. And early in my career, we did a lot of systems that were all one big tank and one big filter and the water circulating all around, and it was great. And then I watched one by those companies go out of business. Not in the first year, not in the second year, but in the fourth or fifth year, when that nasty disease finally raised its head and then got into the system and knocked the entire system out, and that means you're out of business as a general factor. Because by the time you get back to speed, you've lost your customers, probably lost most of your money. So new owner time. This is set up with individual tanks, and then we have what we call blocks, which are simply tanks that are brought together to operate as a unit. That's to increase production. You expose yourself to some disease risk, but you can increase production by 30% by having tanks stocked and have some cross-loading between your filters. Then we go into buildings, and that's buildings are there to protect yourself from things like fire. How many, you would think a wet building wouldn't burn up, but you'd be surprised how many people have gone out for fire. And then there's your facility. And these buildings, also for disease, if you look at disease management, it's great to have buildings that are operated independently with independent people and stuff, and this basically protects you from a total catastrophic loss. So we look at that right off the bat, and I suggest you do that, not for your first system, not for your experimental system, but when you start going commercial scale. Here's the typical layout. This is for a finfish system, but we would do exactly the same thing for you if you talk to us about shrimp. And some of the other speakers have alluded to this. This is our acclimation building right here. This is where your PL10s would come into in this particular topic on shrimp. And basically those animals that come in, this is your principal disease threat to your facility. And if you get a bad batch or you change supplies, you multiple suppliers, then this is where your problem's going to try to penetrate your facility. A lot of times that'll manifest itself in that first few days, and so that's what this building's for, to bring them in, settle them down, check them out, make sure they're healthy. You then risk your fingerling buildings, which are over here, and you move those animals over. And of course, we're going to say you never move one batch of fingerlings into both buildings. If you have a batch, you bring them into one building so you don't lose the other building with it. By the time the fingerlings get up here, or in the case of your PLs, get up to about 1 gram, you're pretty sure that those animals are healthy. In other words, your principal threat to your facility has been stopped. That is penetration from the outside. And then you're going to stock those fingerlings in batches out to a building where this is a block, in this case, 4 tanks that are operated together, and with a means typically we cross-flow them so that you can operate them to get better sharing of the load amongst filters. And we could show you how that it can increase your production by about 30%. And so then, and each building has its own, in this case, it's laid out with its own blower and or mechanical house. We try to design a facility. We're pretty strong in airlift. We put all our blowers outside the building and in a dry room. And then basically, if you need help, you just send a mechanic in there. He doesn't even know it's fish on the other side of the wall, right? And we minimize all points of electronics so we can in here. At some points we'll brag no moving parts, no electronics. If you'll drink the Kool-Aid, we'll take you there. This is a typical room. This one was in North Dakota. Here's your 4 air blowers. That's the only thing that moves in the facility is our air blowers. We use no water pumps in that design. But these air blowers are very critical. They're always positioned in a position where they can draw fresh air into the building. If you do not, and this is North Dakota, so Lord knows they wanted to close those doors in the middle of winter, but we wouldn't let them, you know, because if you close the doors, then they're going to start sucking air that just came out of your tanks, and basically they're full of CO2, and then you're going to put that into your CO2 separation device, and you got no CO2 removal. It just builds up. The fish probably won't die, but the pH will drop, and then you got real problems. Actually, I've been in buildings where I got dizzy from the CO2 in the early days because they had no appreciation of this. So you have to be, here you can draw the door a little bit up and down. You can actually regulate it here in this building, get how much outside to save on heating in the depth of winter. Minus 20 degrees, you need a little bit of room on that air input. The other big thing we found is, this is the Walmart scenario. I got an old Walmart building. I want to put fish in it. Look at all these fish I can put in that. That's an actual case. Actually, more than one actual case. And we do a phase 1, and one of the lists things we say, verify water compatibility of the building. Because if you're anywhere south of South America, north of South America, you're going to have a condensation problem at some part of the year, and this is going to drip off the ceiling like this, and if it can get into your insulation, which typically up here, your building's probably coming down, and that has happened, and with a multi-million-dollar facility where it literally collapsed right down into the tank. So you'll see, if you saw over here at the fish barn that they had that foam sprayed on the inside, you can use plastic liners, but sometimes that makes that building not look so attractive. So that's what I call a sleeper, that if you're not aware of that, it'll get you. It's one of those you really have to watch out for. Here's a popular conversion here. This is a chicken farm in Texas, which is, by the way, there's hundreds of these buildings down there, because it turns out if you disagree with your chicken processor, then you have 8 houses you no longer can use for anything, and you end up selling your property with this liability on it. And actually, the chicken guys have this pretty well down, and they convert pretty easily. And this one is, you're looking at half the building is 2 80,000-gallon tanks. And then you can see the sort of the scale here. And then they did put a little insulation on this one on the top. I'm not sure if that was in there before or not. They took it off to get a little green water on the other side. There's your filters. They dug a pit in the middle for their filters so they could use airlift. These air blowers were there in phase 1, moved outside in phase 2 when they closed the other side of the house. They have 4 80,000 gallons in that one system. This is a tilapia facility. Here's some North Dakota chicken, I think turkey houses in one case here, where it's much tighter. These are smaller houses. They were insulated very heavily. It worked great, except for it's hard to move around in here. It's pretty much you have to walk the food in, you have to walk the fish out, which is something I don't recommend. But again, the houses are compatible. Insulation, in this case, we'll talk about heating. They actually put the heating in the floor, in the concrete, so it worked out pretty good for North Dakota. Another design up there that's actually a lot prettier and more walking space, but a truck could not get into this one, but you could with a small go-kart maybe. We're getting up to more commercial scale. These are million-pound type facilities, and a common feature you'll see in almost all of them is the ability to drive at least a Ford 150 down the center of them, because you're moving tons of food in and you're going to be moving tons of shrimp out. And if you don't have that facility, boy, you're going to regret it. So you got to think about this. At first, it's sort of fun to raise animals. After a while, you're hauling those animals out and you're hauling this in, and you need to really have a way to get in mechanically. So I always look for this as a floor design. Is this a mature facility? Again, these are greenhouses. We put them in, well, I say we work with clients and put them in as far north as Colorado. But the greenhouse people will tell you how far they can go. Greenhouse technology is really great. You just tell them what you want, what temperature range. They'll tell you how much it costs. They'll tell you what liner to use, on and on, because they do so many. Here's a Colorado system. This is raised up from the ground in downtown Denver in this aquaponics system. And again, this was built around them. When we look at cost options, this is generally the cheapest cost option if you can afford to do it. And you probably, if you don't do something, you'll be running green water systems. You'll get a little extra nutrition from the algae, because they will go green unless you shade them like we did in this case. This is a system that was built back in North Carolina some years ago, and I like to show this because of safety considerations. If you're using pure ox, it has to be away from your building and on a slab, and etc. And they have great access here. And then these guys were previously hog farmers, so they knew about moving tons of food in. And so they're set up so it can download directly from a truck into these hoppers, and then they have automatic feeders in this particular facility. But that's another thing to consider. Food storage is a big issue, and particularly in the south when it can get hot. And here, I guess in the summer, it can go sour on you if you're not taking care of it. So they got food storage, and food movement is a big issue. Here's the other side of that house, just showing you a couple features here. And here's that auto feeder system, which is available. The agricultural sector is pretty advanced. If you talk to the right people, you can get that. We have very few facilities actually use this technology, though, because the first indicator of a problem in most applications is behavior of the animals, and people prefer to have somebody going by and casting. But in our shrimp systems, the ones we have, we do use auto feeders to either do all the feeding or supplement the feeding. But here it's a matter of cutting down the labor. There's an air heater in the back. Most of the systems are blown air. It is more energy efficient to heat the water. In that Texas facility I show you, they actually use a boiler to heat the water itself, and that saves a lot in gradient. But these blowers are pretty easy to put in. The North Dakota systems are real serious about heat management. They actually laid the heat exchange units, had a boiler, and put the heat tubes down in the concrete, which worked very well because it's right next to the tanks. I'm going to tell my people simply no metal. If you really do have to use a metal, better be using 316 steel if there's anything salt around, because otherwise it's going to corrode pretty badly. The cheap stainless steel will corrode too. I saw evidence of this in the building we went to yesterday here, the tour. There was a lot of rust and corrosion in that system, and yet the guys that built that building promised the university that that was a salt-proof building, which you could see it sort of cracking at some of the edges and stuff. So, but another thing I stay away from, we don't do any of, is this coated steel, because this is going to happen within a couple of years, and then you've got galvanized or steeled and direct contact with the water, and then when your shrimp start dying, you got to start scratching your head, is it metal toxicity? So we do it simply so you don't have to ask that question. But some people can get around with it. Anyway, that's a summary of my substitute talk right there. But fractal design, that is, really think about disease avoidance, because if it's not a problem today or tomorrow, it's going to be eventually, and for the whole industry at times. So be careful with that. and then those ones that I highlighted. And this is a real sleeper right here, this CO2 thing, because you may not have a problem when you got the windows open, becomes cold day, you close it up, and that's when I start getting the phone calls from up north. My pH is down, what do I do? Open a window. That's to remind me that I'm changing topics. Now I'm going to warn you, I've been asked to summarize stuff that I'd normally cover in four lectures at the university. I'll do it slowly, but the main problem is when I change topics, stop, take a breath, and change your thinking. Okay, otherwise you'll be thinking about the last topic when I've changed topics. Okay. So this is sort of on a nut bag is, okay, so you want to reuse your water and eventually you want to flush your toilet, and I'm on that end of the deal. By the way, where is Andrea? I want to thank you for getting the butt end of this deal, right, so to speak, right? Look, I'm from California. I'm all about using your water until it dries up and you can walk on it. Okay, so we don't discharge from any of our buildings unless we're told to, virtually everywhere, anything but sludge. And we make that thick, really thick if we can, so that it's just because I'm from the desert, right? And that's my sort of our thinking. So we're going to talk about real quickly you reusing water. The things that happen are going to be alkalinity, exhaustion, nitrate accumulation, and refractory organic accumulation. And then I'm going to talk to you about solids management, which is what's happening to the other half of the pellet that you put in there. You put in a pound of feed, and about half of it turns to waste solids immediately, and so we have to talk about that, or you're going to be overwhelmed. So first of all, water does not age. You know, if you're discharging water, it's just because you're afraid of reusing that water. It's not because that water has to be, discharged. That water's been on the planet forever, for in all likelihood, right? So it isn't really the water, it's what you got in it. For shrimp grew out, for shrimp grew out, a couple quick summaries is salt level is going to increase due to evaporation, but it'll just add fresh water and you go back to the right salinity. Sometimes you have to add salt because you have too much spillage. Alkalinity will decline. That's going to kill your first batch of shrimp if you don't listen carefully. Refractory organics will accumulate. Water's brown. The water's not brown. It's got brown stuff in it, right? And then your nitrates will increase. There's been a lot of allusion to that here. One term I'm going to use is cumulative feed burden. Oh, I keep pushing the wrong key there. The cumulative feed burden is how much water has been reused, and it's measured in grams per cubic meter of water. That's how many grams of feed you've applied per cubic foot of water. A typical RAS, freshwater RAS, will reuse about one that will apply 1,000 grams per cubic meter or milligrams per liter before they discharge their water. My friend out in California, he runs at 100,000 grams per cubic meter and only discharges when he has to. Well, of course, his strategy is pretty simple. If he goes over that, the quantity of water that he's discharging, all of a sudden he's subject to environmental regulations. If he can keep it down, he's not subject. So it turns out there in the depths of Los Angeles, that's a big deal. Most of the shrimp systems that you see that are up in that 100,000, 50,000 level, they're pretty high if you're trying to do a closed application. Down in our country, down in Florida and stuff where we can discharge salt, and some guys are running a lot less because they can leak out the back door, but I don't think that's going to work up here. Okay, so we are engineers, so we have to have some numbers. I'll spare you the equations, but we basically go into literature and we look at a 5 kilogram per cubic meter stocking density, sort of the average. And then we look at the shrimp growth, and so here's your little guys start out little. Let's start with 1 gram here, assuming a 1 gram stocking, so that's that second stage of grow out in the last 90 days. And then basically here's your grow out curve off these literatures, and we've seen similar. And as those animals grow, 2 things happen. First, your percent feed declines. That is, the percent of body weight that you feed every area is declining. And then your feed rate, when multiplied, this percent multiplied by the size of your shrimp, you get a sludge production. This is waste sludge production. Feces, if you like, it's the feces from the animal But a lot of, in this case, is a lot of just food that wasn't eaten in the first case because they're not particularly clean eaters. And it builds up like this, okay? And so that's over your 90 days. So that's sort of our background for this. That's the problem is feed, folks. If you don't feed anything, then we're not going to have any problems I'm talking about. Alkalinity is not going to exhaust, no color, no problem. But if you come to me, I'm going to first thing ask you is how much you're feeding. What % protein? And I really don't need to know what you're doing beyond that to get you good water quality, because everything is sort of the same after that to the filter guy, or the biofloc guy, I'd say in a sense. So I was sort of lamenting the lack of these fundamentals here, so here I go real quick. You put in feed into a fish, or in this case shrimp, and out comes ammonia, and basically that comes out at 35% protein, is 30 grams of nitrogen as ammonia, and that's total ammonia nitrogen, by the way. I was a little sloppy in this slide. And that's going to be the case, and that's going to form the ammonia that's going to try to build up. And that's from the protein metabolism of the fish is where that ammonia comes from. So 30 grams per kilogram is our start of that. The ammonia is a toxin at a few milligrams per liter. In this group, you can probably come up with a big argument about what that is. The biologists like to talk about unionized ammonia, which is the correct term to use, but engineers can't deal with that, so we just talk about total ammonia nitrogen, which depending on your pH is basically going to start causing problems in most animals at a couple parts per million, 2 milligrams per liter. With shrimp are more tolerant and they can go up, so maybe, I don't know, again, I saw two extremes here. I don't care what the ammonia is it almost has to be non-existent. So that's a philosophical difference. But they're tolerant, shrimp are pretty tolerant. So I would tell our people, if you're above about 2 milligrams per liter, you got a balanced problem in your filter system, you better get on it. But I wouldn't probably kill the shrimp. So nitrifier bacteria have enzymes that can unlock the energy that's in that ammonia. So you can't stop them if you want to. When I was conducting research at the university, I had to kill or clean the backs of some animals all the time because the nitrifiers grow on the back of the turtles and the crawfish and all that, and they would nitrify so fast it ruined my experiment, which I'd do with that. So it's not hard, folks. Just give these bacteria half a chance, and they'll go crazy. They'll take that problem away for you. And again, these guys are experts here, so they sort of trivialize this, but I got to tell you, it's not trivial. There's a lot of animals die because of this. Not if you're an expert, but when you're a starter. The nitrifiers take ammonia from ammonia to nitrite to nitrate, where nitrate is stable under aerobic conditions. It'll stay there for days, it'll stay there for weeks, it'll stay there for years. If it gets in your groundwater, it'll poison you, several years later or a decade later. It's very stable. It has no inclination to go. Okay? And it's toxic, and it's hard to say. Again, I'm saying 300 to 500 is a general statement. I don't know exactly. I did know a month ago what it was for shrimp, but I've since forgotten. I guess it's my age. I circle this because that's one of our topics. They consume alkalinity. They're slow-growing animals. You have to acclimate them. They have to have oxygen, I say, above 2 milligrams per liter for effective denitrification. And then the alkalinity has to be above about 100 before you start getting into trouble with pH, which I found is a problem. If you're running 25% salinity, then you might not have 100 to start with, so you might want to add some alkalinity. And the pH generally we want to keep above 7. At 6.8, you've lost 50% of your nitrification capacity. And by the time you get down to 6.3, 6.4, it's pretty well knocked down. So there's not much of a difference. So here we go. You got your system, and you set it up, and you load it with your 1 gram shrimp, and you're bipping along. Here you start, and you're watching your pH every day here probably and getting real intense, and then after a couple of weeks, no problem, so I don't need to do that every day, and you stop doing it. And then basically and this has happened so many times, and then after a while, all of a sudden there your pH problems start, but then you're probably not even checking that anymore. You're not particularly concerned about it, no problems, I'm still 6.8. But by day 30, you have zero alkalinity, you have zero nitrification, and your animals are about to be dead. Okay, so this is a sneaker on you. If you're a first-timer, you're not going to bother the first 2, 3, 4 weeks, but watch out for that next month, because you're probably going to have a crisis just for this one reason. So about here, an alert person says, I get down to 100, I don't want to make 80, which is critical, so I'm going to dose at 100, and I'm going to just add sodium bicarbonate is what I recommend for beginners, and I'm going to add that to get it back up to about 150, and then it's going to drift down, and then I'm going to add it and drift down. And generally, I'll trigger this on an alkalinity test kit, like aquarium test kit, or I'll measure pH, just watch the pH approach 7, I got to get up to 7.5. But another sneaker here is watch when you're talking to people, look at this interval. It's getting smaller and smaller and shorter and shorter and shorter as we go along. So by the time you get down here, you have to be doing that twice a week. All right, so it becomes a regular demand. A quarter pound of bicarb has to be added for each pound of feed. A quarter pound per pound. Now, a soda ash is stronger. You can add less, but you're actually going to pay the same amount. Lime is a lot cheaper, but boy, if you overdose, you've got a tank of dead fish, so I wouldn't recommend that for beginners, although there are some good arguments that in the long run that might be the best option. However, with biofloc systems, be careful because you will be producing calcium carbonate and weighing your flock down pretty quick. So that's something to be considered. If you have denitrification, we'll talk about in a minute, then that everything's stretched out to about twice the interval, and so then you're actually real asleep before you get in trouble. Okay, but denitrification does not replace all the alkalinity that's lost. It replaces about half, in some cases a little bit more than that, but not all. So that process, it will stretch it out. So summary, alkaline declines as the shrimp grow, and let's see, correct it, and denitrification improves it. So that's the alkalinity summary. So if you do that, you can reuse water now for a month. We extended it that far, right? So it's basically salt water is good for a month. No harm, by the way. Now we go back to our common reuse carrier. That's a CBF term I was talking about, cumulative feed burden. And here's your different levels. And this is what it looks like. And you can see it happen. And this is a larval system. This is the same facility, by the way, an ornamental fish system. A larval system, probably 1,000. There's your typical freshwater grow out because they can discharge the water, they do. And so it's probably 10,000 milligrams. And there's your marine 100,000 milligram water. And what you're seeing there is you're seeing the organic material that the bacteria cannot effectively attack. Okay, this is a fixed film system, so the water, there's no solids in that. The browning of the water is what's called refractory organics. It's basically the residuals of the material that the bacteria can't attack. So the longer you use the water, the browner it gets. Okay? We generally, here's an actual system. This is the kind of system we like to see. Okay. Now I understand talking to some folks here that might stimulate some long-term Vibrio problems and this, that, but as a general observation, in most species it causes no problems. But it sort of might insult your visionary senses. Or more importantly, your customer that comes in to look at what he's buying in your tanks, right? So there's an easy solution, and it's getting cheaper every day, and that's ozone. Ozone can take that water and take it from that dark brown to that almost swimming pool clear in probably 24 hours or maybe a day or two. So it's very, very effective. It's liquid fire if you want to think about it, and think of that as residual wood chips, and it's going to basically take it out. The ozone generators are coming down in price. You can do this at the end of the season between batches with no animals, and then it's no problem. You have to be careful to ventilate because the ozone can get you too, right? So there's some tricks here, but there's no problem doing it. We do it at our facility because I simply say the customers are coming in. If it gets brown, turn that thing on. If it's clear, turn it off. And by the way, if your water's brown, you generally will not hurt your animals because the brown material in the water will absorb the ozone before the animals do. So I tell my people to keep it yellow, not first yellow. If you do that, if you just try to do all the ozone, it's going to cost you just for color control about 5 cents per pound of animals, most of that in energy. Okay, so yeah, is that per kilogram? I can't see the C. Per kilogram, sorry, for the shrimp or fish, just to handle color. That gives you an idea about the cost of doing that, about 5 cents per kilogram. If you're going to do that, start with batch operation because that's almost idiot-proof. Turn it on, ventilate it. When it gets crystal clear, turn it off. Yeah. We do it continuously, but there's some tricks to that. So there's a lot of technology out there. Okay, stop, changers. Now go back to nitrate. Change your thinking. We're going back to nitrate. So we nitrified and we put the nitrate. And nitrate, the animals are relatively insensitive to. Shrimp and other animals probably could tolerate upward of 1,000, although you might have growth problems and that type of stuff. You know, some marine animals are highly sensitive, as low as 50 milligrams per liter. And but generally most fish, it's pretty inert stuff. By the way, it'll get you about 10 milligrams per liter if you drink it and you're pregnant. That's metho, if I can remember that, blue baby syndrome. And it binds with your, if it's in your drinking water, binds with your hemoglobin, and it can't transport oxygen to a baby properly if you're pregnant. So it's heavily regulated. That's probably what you really need to know, regardless of what its standards are. If you try to discharge it, you might run into a real wall. Okay, it depends on what state you're in. Oh, and that's discounting the salt. That's your other problem. Anyway, this is an uphill, this is an uphill battle. Requires energy. And it deals with electron metabolism. And basically, if a bacteria wants to make a living when oxygen disappears, it's got to figure where to put an electron, and it can put it on the nitrate. It actually has to force it in, and it goes uphill. The nitrogen gas bubbles off, end of problem. Nitrogen, you have no history of your nitrogen addition then. Okay. And this is almost, I see a lot of complicated talks on it, but to me it's pretty idiot-proof. Heterotrophic bacteria are fast-growing. All you got to do is lower the oxygen and make sure there's some nitrate there, and then give the bacteria something to eat. Sugars, starches, methanol, ethanol. I'll show you bioplastics, and of course, look at this quiet one down the end. That's going to be pretty important for you, manure, because guess what? You're producing, we're going to see in the next little talk, a ton of it. So that's actually a source we're going to go after. Now, just a quick short course on denitrification, just sort of basics. By the way, this paper was an excellent paper, Boley in 2000, right here in Aquaculture Engineering. If you read that, you pretty know what the state of the art was. But there's two basic ways of denitrifying. This is the one that's dominated conventional denitrification. You have a fixed film reactor, and you can also do this biofloc, moving bed reactors, fluidized beds, bead filters, it doesn't matter. Any bioreactor works really well. And you add an external carbon source dissolved in the water, and the bacteria grab it from the water, and they convert it to nitrogen gas. All right. So the problem with this one is you have to dose, particularly if you're doing it continuously, and you have to dose the right amount. If you don't dose enough, your nitrate goes up. If you dose too much, you're going to get sugar into your system. Well, in this case, it's going to generate more biofloc and on, and maybe it's not all bad for a biofloc system. For a fixed film system, that's okay to a point, but it causes a problem. The other one works a different way. You have a bioplastic or wood chip in the center here, and basically it is the carbon source. The film grows around it. It takes the carbon from the inside and the nitrogen from the outside, so there is no transfer of the carbon to the tank. And I'm going to call this passive denitrification, because those pellets don't do anything unless there's nitrogen available. So when you have high nitrate, they process. When you don't, they go passive. Okay, and so in other words, you can put a passive bed there and it'll nitrify when you need it and not when you don't. Pardon my language, is idiot-proof, and I need that kind of technology myself many days, right? So that's not really done a lot now, but I think you're going to see it occurring more and more. Why it's not done a lot is here, Boley did back in 2000 a cost of processing the nitrogen per kilogram here, and these bioplastics back then were 10 times more expensive than methanol and ethanol. But now it's about 2.5. It's closing in pretty quick. And so look for that. You'll see it coming out. This is a redox ladder, just so you can say you've read this, and you'll become an expert in chemistry if you've seen this graph. Look, the electron, I always like to take this real quick, is, why did it do that? The electrons are attracted to these different chemicals like oxygen, like a magnet would attract metal. And in the compounds that attract the metal the most, or the electrons, is up here. As long as oxygen is present, you're going to get nitrification, because the enzymes for that then move that way, right? It's the easiest way to make energy out of anything is to move it to oxygen, get a good spark when you do that, so to speak. As the oxygen gets depleted, that option is no longer available, so a lot of bacteria heterotrophs will switch to using nitrate, as I showed as electron acceptor. If you run out of nitrate, you go to sulfides, is the next one. Sulfate was the next one for electron acceptor. And by the way, it produces hydrogen sulfide, which kills all your shrimp. Okay, so you have to, that's why you're going to be a little careful with dosing, and you add too much sugar, you use up all the nitrates, then you get sulfides. Again, I don't want to give you the impression it's hard. I just want you to let you sort of learn the general trend of things. So all you got to do, in my opinion, like with our bead filters, all you got to get denitrification is get the DO under 0.2 in the filter, and it'll switch on you and start denitrifying, because the bacteria are going to make a living however they can. Not as much energy that way, though, for them, so they'll get oxygen if they can. So here comes the Israelis, who were in desperate water conditions and desperate economic conditions well ahead of us, and they're also great scientists, and they start studying this problem out in the desert. How can they get the most fish and the most shrimp and the most marine fish out of the least water? And they come over to the United States. Dr. Van Ryn in particular comes over. Let's see, I'm really messing up. He comes over and says, hey, you dummies, and he's a good friend of mine, I can say that. You know, you got a system that is all aerobic. You got no place for anaerobic digestion process. The Earth has this everywhere. It's the principal driving force, and you're designing a system without that. You need to add that anaerobic component. And then, so he designs a system. This is his first one here. This is, and again, even he was not as brilliant as he was, and he's a brilliant guy. His idea was to take the water off the animals here, move it to a splitting case. This is like a disc. This thing does not. And put it through a sedimentation tank, and then take the nitrate to a fluidized bed. That's that drip the ethanol type system in, right? And then bring that in and then circulate through an aerobic system and back, and you've got both of the major components on the Earth. What he didn't anticipate, and he was honest about that when he gave this presentation, is none of the nitrate that he was trying to get to these beds could penetrate the sedimentation basin. Because it turns out manure is a carbon source, and it takes out the oxygen real quick, and it looks for somewhere else. They look for somewhere else to put the electrons, and there it is. It's nitrate, and it goes pretty quick. And so now the recommended design, which I'm going to recommend you today to look at seriously because of the cost and the simplicity, is to go into your building, and this is Moses. Dr. Moses did another system, a marine system in this case. Here's your fingerling system, and then here's your main system. And what he's going to do, I think this will work if I push this. Let's see. Yeah, wow. What he did is he takes his water here, which he's filtering biologically and everything, and then he takes his sludge over here and dumps it in this sludge basin, and that's a dilute sludge, so it's a bunch of water with a little solids, dumps into sedimentation basin. The sediments are captured here, and then he takes what comes off that, and if he has to discharge it, he discharges it, but most of what he does is he puts it right back, that water right back in the system. So he basically is losing no salt in this case. He's denitrifying, as it turns out, based on what's happening, and we see mostly now. He's denitrifying over here in this sedimentation basin. And he's extending his water use now to months at high densities, 2 months. Now, if he wants to go to years, then he puts one more system in there. He puts a small denitrifier with one of the traditional designs in there to supplement the sedimentation tank if it doesn't do it. But he only uses that if he needs it and when he needs it. And in the case of shrimp, for it looks like that, it would be years in order to get moving the years of reuse of water. But the manure costs you nothing. And the reactor costs you little. It's just a tank, and the water flows over the top. And you're going to have to do it anyway. You're going to have that sedimentation tank and stabilize that sludge anyway. So it's a no-cost option. You're going to pay me to do that, as you see in my sludge digestion step. Next, you're going to have to do that anyway. in almost all cases. Well, here's a summary for nitrate. I believe denitrification is easier than nitrification. So if you can produce the nitrate to begin with, it's very easy to produce or get rid of the nitrate. Just provide a carbon source and lower the DO below 0.5 and it'll take over. They make a living. The bugs make a living that way. You don't have to do much. There's ways you can mess it up, but they're pretty rare. Now we've taken that growth curve and we start looking at the sludge discharge, and I've separated this to your two compounds. This is a fixed film system, which is the type we specialize in, and this is a biofloc system, and this, again, remember, is at 5 kilograms per cubic meter. It's standard, what we think is the standard grow-out densities. And you see, first of all, in your biofloc system, this is sludge coming out of the tank. A fixed film system is going to start producing sludge the day you turn it on, but a biofloc system is not going to start producing sludge until you start having to crop the solids. We just heard 350, I think, was a deadline. Some people said 500. I think we used 400 for this particular line. Then they're going to start producing solids, and this is what we're talking about here is sludge, the solids, the manure. Yeah, basically it's the same as cow manure, pig manure in terms of its chemical constituents, but it's very dilute. A lot of water's coming with it. So your first step is to separate the water. This is the sequence for handling sludge. Feed goes in the shrimp, shrimp produce feces. In the biofloc systems go to biofloc, and by the way, folks, most of us, except for the shrimp industry, call that a sludge digester. Extended aeration is what we call it, and you're consuming the waste from the animal there. And then you're going to disludge. So if you have a biofloc system, your sludge production is going to be about half out of the tank, about half of what you're going to get out of a fixed film system or a straight clarifier. But when you put in a sludge digester, in either case, then this one is going to make up for the difference, and you end up with a disposal problem about the same, about 300 gallons of concentrated sludge, 4% sludge, per 1,000 pounds of shrimp that you produce. Doesn't seem like a lot, but start calculating how many 1,000 pounds you want to sell to make money, and pretty soon you can see where the shrimp industry is ultimately going is the same place the pig farmers are. You got a big problem out back, and it's going to start inhibiting the whole industry at some point. And when you start talking about producing hundreds of thousands of pounds of shrimp, you've got a big, big problem. Right now, there's enough of you, and you're small enough, in most cases, that you can get away with this, and I think it'll be a good start for the industry. You have to eliminate, in order to just get rid of the sludge, you got to eliminate the odor, you got to improve its physical characteristics, and you got to reduce its volume by as much as 70 to 90%. So that's the sludge itself. That's not the water that comes out, that's the actual solids we're talking about there. In your case, you got one more problem, salt. You're gonna have to somehow unsalty it. I know, I'm a professor, I could create words, right? Typical open RAS works like this. They have the facility, they discharge water and sludge into an outdoor pit, and then the water and some water, and they put that into land application. When it's dry, they put it and they spread it on their fields. They discharge the bulk water out this side, and oops, now they run into a problem because the state notices their discharge and they have to go through the permit process. That's enough to scare most people to death. So what they do is as a closed RAS, which is allowed in most states, is you basically have the RS facility, you discharge water here and sludge here, and you land apply both to your land. But it must not roll off your property, unless it's raining, and then we sort of wink, and some can come off, which is it's pretty handy to have a wink, right? And that's the typical, most of our RAS are these closed systems. Yeah, I'm almost there. He's saying I've only got 5 minutes, and I used to teach with a 45-minute lecture slot, so don't worry about that. Here's a nice application. Back to that system I was looking before, a pig farmer before, by the way, so he knew what he was up against. They have a microscreen inside, and they have a hydrocyclone they put into an anaerobic sludge pit, which is covered to prevent odor problems, and et cetera. And it digests down there. The water, you'll see in a minute where it goes. It goes to a little pond on his property or on the grass around it. And then they periodically pump the sludge with a sludge pump out on the grass. That's really sweet, folks, but you can't do that, all right, because you're doing saltwater shrimp. There's this thing called sodium absorption ratio that looks at soils and interaction, the relation of sodium, calcium, magnesium, and I can guarantee you salt water is not compatible with that. If you try to put your salt in there on your land, you're going to end up with a lot of not only dead plants, but dead soil too. So this is regulated in some places, and your ag consultants can talk to you about this because they're well of it. Anybody in the West is very aware of it. So you got your sludge disposal pit. You can have one of those, and you may or may not have to line it depending on the state, but you can have one of this, and this is, if you're a small operator, this will handle most of your problems, right? If you're up north, based on our experiences, I guess he was going to turn my thing off. You might want to cover it because in North Dakota, those facilities I showed you, the pit froze solid in the winter, and you just started sludge on top of it, and you get a big mountain of manure, politely said, that will thaw suddenly in the spring. So you might want to cover it, and so you have to keep it at least flowing in the winter. But you can, I think, get away with this. Use the Israeli model. This is what I would suggest. You use the original model to locally digest your sludge and denitrify. Take that stabilized sludge and move it out to an external pit where it will degrade by another 50% or 79% over months. And then use rainwater maybe to fall on that pit because it'll have virtually no runoff itself. And use the rainwater to overflow to a pond on your facility, and then it can sneak out during a big rainstorm. And use that rainwater to dilute the salts out. We're not going to let much out here, by the way. It's going to be very, very small in water, but that might be a solution for you. The other solution in some bigger facilities, we would look at solutions like this, which is take that sludge that's been digested and put it on a belt separator, and they have small ones, and that produces a dry cake. You can literally pick that up, and you can have it trucked to a landfill or make even less of a problem outside if you try to dispose it on your site. But and this will take most salt out of it too, by the way. But the salt's the unique issue there. And that's the end of my, am I okay now? Andrew, you're not nervous. I got it, made it, right? Thank you.